All right, good morning, everyone. My name is Tevin. I'm the Kickstart executive here at Pathway CTM. I'll be facilitating your session today. Just before I hand over to John, Joe, and Will, I want to turn your attention to our Q&A box at the bottom of your screen. If you have any burning questions, please do feel free to put some questions into that box. Otherwise, at the end of the session, we'll have time for a Q&A where you'll be able to ask any questions you like and get answers for it, hopefully. And yeah, without further ado, John, Joe, Will, over to you guys.
Thanks, Tevin. Good morning, everybody. Delighted to be able to do this with you today. Me and my team are going to hopefully explain to you a little bit about how physics can be used in the workplace and how we use it in our day-to-day role. We're pretty new to this. We did a session earlier on this morning in a similar way, but it's not something that we do day to day. So bear with us, and hopefully you can enjoy what we have prepared. As Tevin said, if you've got any questions, post those in the Q&A box, and we will deal with those either as we go, if Tevin thinks it's appropriate, or at the end of the session. Just by way of a brief introduction of what we're going to talk about today, this presentation is based with a physics angle. We're on a physics class, I guess, for you guys today, and what we're trying to do is to explain how, by an indication of how where physics plays a part in what we do as our daily life as engineers. We'll give you a bit of an introduction to our company and what we do generally, and also explain how physics plays a huge part in building services and the role that we play in buildings. And then also give you some guidance on how, if you have an interest in physics, that might be converted into some career decisions that you take, and particularly how it's affected Joe and Will. We'll get onto that a bit later on today. So who are we, first of all? So Joe, Will and myself work for Environmental Services Design. We are a firm of building services engineers, and we are involved here through Pathways and Brent on the project at South Kilburn. We'll explain a bit more about our involvement on that later on today. Will is a graduate mechanical building services engineer. Joe is an electrical building services engineer, and I'm a director of ESD with a mechanical building services background. We are a firm of consulting engineers, and we employ mechanical and electrical engineers at different grades, from apprenticeships right the way through to chartered engineers. But we also have within our team CAD draftsmen, 3D modelers, building physicians, and general support staff as well. So what do building services engineers do? It may be a term that's not very familiar to you as building services engineer, but we try and explain it best as being the role that we undertake is that we design the systems that make buildings become active. I guess most of you will have be familiar with what an architect does, in that they design how a building looks and fits within its local environment, or how it stands out if it's an iconic building. Often architects work with structural engineers who help to design foundations and to support how the building stands up. But building services engineers work in the same team, and we are professional designers, and we design the systems that are often hidden away in buildings, behind walls and behind ceilings and in plant rooms. And those systems extend from heating, ventilation, air conditioning, lighting, power, Wi-Fi, CCTV, security, all the systems that you take for granted perhaps in a building, but ultimately the building wouldn't work without them. The role of building service engineers has changed quite a bit in my time in the industry, and certainly over the last 20 to 30 years, due to the increased awareness of global warming. Carbon emissions are a huge issue that I'm sure all of you are aware of. It's regularly held in the news and in discussion around the country. And the control of carbon emissions and reduction to help mitigate the effects of the world's overheating is something that's greatly influenced by building services engineers. This slide shows you, buildings contribute to 50% of all carbon emissions that cause climate change. And we're acting now to help to reduce this. There's various documents and government legislation that are being drafted and have been issued in recent years that start to require all buildings to be what we call net zero carbon. So that is whereby the carbon emissions that they take and use to run a building are offset by renewable energy. So we are tasked to make buildings much more carbon and energy efficient to bring that figure of 50% down to zero ultimately. That will still leave lots of problems with existing buildings, but certainly on new buildings, the move is taking place now. The aims ultimately, by reducing carbon down to net zero, is still to keep the buildings obviously comfortable, safe places to work and live, but using ever more efficient equipment and system design techniques. So the types of products that we get involved with and systems we design now include the likes of LED lighting, photovoltaic solar panels, electric heat pumps to be used for generating heat in place of boilers in a more efficient way, heat recovery on ventilation systems to capture the heat that's often discharged from buildings, and the use of solar panels to generate hot water for buildings, and also passive systems whereby we use the building structure to cool a building overnight using cool and nighttime air to save on the energy required for air conditioning the next day. So some of these may be new techniques and new terms to you, but they're going to become commonplace and easily recognised through a lot of your adult life, would we expect, yeah. In terms of the scheme at South Kilburn, this is a scheme where ESD have been employed by Brent Council with the architects, Pollard, Thomas Edwards, and the rest of the designers across 3 of the phases. It's a multi-phase redevelopment at South Kilburn. We've been employed on 3 of those phases over the last 4 years, and within those 3 phases, we will deliver over 600 new homes. Our role certainly in the pre-planning stage of the scheme is to look at the building's anticipated carbon emissions and help to reduce those, make them comply with the government legislation I mentioned before, and the legislation that's imposed by Greater London Authority. And then we'll look at the planning of energy distribution around the site. And at South Kilburn, it's quite exciting for us because they have a district heating system that runs with low carbon technology and provides heat to all the buildings. We'll look very detailed way at how we stop the new dwellings from overheating. The increase in external temperatures through global warming causes a huge problem for residential overheating. That's something we have to design out at an early stage. And then ultimately planning and designing the systems for each of the new buildings and the new homes within them, everything from TV outlets, Wi-Fi, power, heating, ventilation that we've touched on before. What I'm going to do now is just pass over to Joe and Will, who are going to hopefully give a bit more of an explanation as to where we use physics in some of the work that we do.
Thanks, John. Hi, it's Joe Lingard. So as John was just saying, physics, science and maths, they really are an integral part of engineering. It underpins everything we do really in the design and calculation aspects of the job. There's different projects, different designs and different engineering. They're all going to be based on fundamentals found in physics. So we use different calculations for different projects. If you're a structural engineer, you'll be doing a different calculation to an electrical engineer, and likewise mechanical. But it all draws back to the basic principles of physics and maths and science, and it's wrapped up in calculation software tools now, and it makes our lives a lot easier. But it's just getting that across. It's fundamental knowledge essentially at this early stage. So, you know, we might what calculations and formulas do we need to use, and why do we need to use them? So, calculating voltage drop for electrical systems to ensure that the system is as energy efficient as it can be. Calculating light emissions from different sources, whether that's internal or external lighting. Calculate the thermal transfer between materials, to calculate heat losses and gains from buildings. We calculate pressure losses in pipes and in air ducts so we can size pumps and the pipe work properly. So yeah, I'm going to pass you over to Will now. He's got some more examples of physics equations that he's going to just run through quickly.
So yeah, I'm Will, and unlike Joe, I'm a mechanical engineer, which means I deal with more like the heating and the cooling and the ventilation side of buildings with stuff like that rather than the electrics. And so we have to use some equations that you can see on here. And like the one on the top left, the specific heat capacity, that's the most basic, or that's the most fundamental common formula that I use in my day-to-day life, as it just works out how energy equates to different mass and temperature. And we use that fundamentally for working out how much water and stuff needs to go down a pipe. We also use more complicated, like you might not know it, but that's Bernoulli's equation, and it relates how fluids in pipes and how it relates pressure and velocity and the amount of water that's going down the pipe. We can use that as the first principle, and we can rearrange it, and we can use it to get the equation in the bottom left, which is the equation we use for an orifice plate. An orifice plate is just something in a pipe that you can use to measure the flow down the pipe, and it uses the difference in pressure at 2 different points, 2 different widths. It'd be quite hard to have to do that every time you needed to measure the amount of water going down a pipe. So we don't do the first principles every time. We take that, we put in some software, or we put in a table, and we can then just use the pipe size and the pressure difference to make it easier for us to do stuff and not have to just go straight back to the complicated equations we can use. If you want to move on, John.
Yes, there's another example here of how we use physics. This is in electrical engineering. So we've got Ohm's law and a power equation. It's used to calculate the voltage, resistance, current in electrical circuits. And some of this work was done by a German physicist, George Ohm, back in 1827, and it still holds true today. This law, and it's used daily in electrical design tasks to calculate how much power a circuit has or needs, and we use it to size cables, protected devices, carry out load assessments, all sorts. You can analyse systems, make sure that they're operating correctly. It's not just used in building services, it'll be used in electronics as well, and a wide range of topics. So these form the foundation of first principles, but as engineers, you need to have that basic understanding of them. And as Will alluded to, the combining design tools and software so that we can carry out our tasks quicker. We're not having to go back and do complicated equations all the time. The standard tables and design software that helps us do that, but it's based on these first principles that we're showing you today. Move on to the next slide. There's another example here, physics and mathematical equation used in lighting design to calculate the lighting levels in a room or space, and that's the inverse square law. Basic intensity of light decreases with the distance from the source. So we can, using this equation and others like it, we can calculate the amount of lux or light intensity on a surface at a specified distance. So these formulas, equations, form the backbone of the software that we now use. We'll generate a 3D model nowadays, and we can position lighting in certain areas to make sure that we're achieving the levels that we need. Next slide, we've got some more software tools.
Yeah, sometimes the projects we work on get more complicated. So this is an example of something called a CFD, or computational fluid dynamics, where you actually model how the air will flow and how the heat around the building will flow. And so for this, it's a project up in the University of Salford, where they're wanting to build a test chamber where you can heat or cool the room between -20 degrees and 40 degrees. And then they can build a house in the middle of this chamber and test how energy efficient and well built it is for different locations around the world. So they want this to be very stable and as if it's in a lab. And so we need to make sure that the way we're serving this building with our mechanical services and electrical, that it is very stable environment. And the difference between the two images is, you see, if we put a 3 kilowatt heater in the bottom left of that bottom there, 3 kilowatts, that's roughly about a kettle. But you can see how just adding something small can drastically affect how the building, the flow of the air and temperature around the building. And so we need to take stuff like that into account when we are designing buildings.
Great, so yeah, just another application of the software tools we use. This is a lighting software that we use on projects. So the top image is the output of the calculation. Basically, you set the calculation up, it'll give you an output of data that you need to just interpret really and make sure it's hitting your specified levels. You'll work to design guides and criteria. So in this particular project down in Norfolk County Council Chambers, the large refurb project, and they had a large marble wall. We were providing internal lighting to that space. We wanted to make sure that it was well lit, but we weren't going to be having glare issues from the marble wall. So we've set the calculation up, as you can see, and we've specified certain calculation planes, if you will, at different locations. And this is based on similar equations to what we highlighted before. It's just another way that it's applied to this sort of software, and it's easy to manipulate. Once you've built the model, you can play around with the light positions, until you get the desired outcome, basically. And our job would be to then produce drawings in CAD or Revit, so an electrician can go and install that lighting where it needs to go. We're going to move over to some examples now. Will's just going to run through.
I said earlier that the specific heat capacity equation is the most common equations that we as mechanical engineers use. So this is just a quick example of how we'd use it. I don't know if you've got a pen and paper or a calculator and want to try and work out as we go, but I'll talk through it anyway. So what we're thinking of here is if we've got 2.8 kilograms of water flowing down a pipe, and we know that the water's flowing at, say, 80 degrees and coming back at 70, so there's a difference of 10 Kelvin or degrees. We want to work out how much heat that is depositing to, say, the radiators or the other equipment that's at the end of the line. So we can then use this Q equals MC delta T equation. So in this, the Q would be the energy or the power that we're getting at the radiators. The mass is the 2.8 kilograms of water. Specific heat is given for a different material, so 4.182. And the delta T is the difference in the flow and return, which is 10 degrees. So if you put those numbers into the formula, you'll get the 117 kilowatts value. So we can use this to work out how much, well, if we know the amount of energy, we know how much water we will need to go down the pipe, which then can then help us size this heating systems. So yeah, as you can see here, so this is a schematic that we draw which shows what we're having in the building. So you can see we've got some radiators. Those square-looking things are radiators, and those will be in the rooms. And then we've got a heating flow and return pipe going out, and then there's a big pipe going up and down the building. And then you can see on the very left-hand side we've got a pump, which is what pumps the water around the building. Around the drawing, you can see these numbers on this cross thing. That's what we call a crosshair, and that's what we use to detail what size pipe and flow needs to go down each pipe. So if you look at the bottom right, we've got an example of what the crosshair will contain. So the flow rate is what we can work out with using Q equals MC delta T. That's the M. The pipe size, that's how big the pipe is. And the higher the flow, obviously the higher the pipe size. From, say, the equations we saw earlier, you'll know that for a given flow rate down a pipe, the water is going to be moving at a certain velocity or speed, so we don't need that to be too high, or the pipe work will be too noisy and rattle about. And then the other quite important bit is the number in the bottom right. As more water tries to pass down a pipe, or a pipe's too small, it'll have a pressure drop that's too high, meaning it has to work harder to try and get the water around the system. So the way you reduce that is you make the pipe bigger, and you've got to try and balance between making pipes too big and costing too much there, and making your pump too big, because with a higher pressure drop you need a bigger pump, which is less energy efficient. And so this is all part of the balance we're trying to do with increasing the energy efficiency of the buildings. But that's just an example of a schematic that we would produce. We were talking about Q equals MC delta T, and we can work out what the Q is, what the energy that you need to put in a room to keep it hot. You can see the image at the top left. You can lose heat through stuff like windows, walls, doors, the ground, everything. Heat can go out. But you'll also gain heat through the sun and equipment. So you need to size that heater in the room to be. And we have a complicated 3D model we can build, and then we input what type of walls and stuff it is, and it'll tell us how much heat we need to put in to keep it the right temperature. But even if you do keep the room the right temperature, it's not as simple as that. There's convection and other things that we need to take into account. Say a radiator doesn't just heat a space uniformly. It's the hot air will rise from the radiator to the top of the room and drag cold air underneath, which will create like a convection current around the room. Yeah.
Thanks, Will. I mean, it's just interesting that the interaction between these calculations, as Will's explained, the formula we use very frequently, Q equals MC CP delta T. The starting point for the use of that calculation is usually calculating heat losses or heat gains. That's one of the very first calculations we do on any project, to establish how much heat we need into a room or a building or a space, either to keep it warm in the winter, or alternatively how much heat we need to take out to keep it cooler in the summer. And then we can apply that into this formula, the Q, to then calculate how much water needs to pass around the system, that then feeds into this schematic that we'll explain. So everything's kind of interrelated on that, particularly on those elements of the scheme design. Yeah. Well, the other aspect that we can start to look at with the involved modelling techniques that we have now is to see how a building sits on a site. So this is a typical project that we've got with a sort of 4 or 5 story building. It is a university building actually, and as we build the geometry of the building into the model, we can then look at what the sun path looks like around it, and determine whether the building's in the right location on the site by moving the building onto a different orientation, or actually just position it in a different part of the site. That could change the benefits or the problems that we have from having the sun on the wrong or the right pathway around the building. It also help with determining the best use of things like solar photovoltaics and solar water heating. This all helps to increase the influence that building services engineers have on the architecture of buildings, not just on the systems within them. Ultimately, undertaking all the calculations, the physics and the modelling that we do, we then have to translate that into a series of design work that can be fed to the contractors to allow systems to be built. These two images show you the new Riverside stand at Fulham Football Club. This is the project that we're involved in. We're detailing the design of the systems on this project. And the image on the right-hand side, you can see the wall stand there with the roof and the terracing for the seats. And the image on the left-hand side, it shows you all the systems that are hidden away inside the building. We draw these in 3D Revit design that allows us to make sure that all the systems fit within the building and that they don't clash with concrete and steel work, and that they're all contained within the roof. And then we use this 3D model to create drawings that can be used on site by the electricians, the pipe fitters, the ductwork contractors, by undertaking this type of design before the installation, it helps to eliminate problems on site. It helps to keep the time that the build takes down to a minimum as well, by undertaking all the design work up front. So just that gives you a bit of an oversight as to what we do. I thought it'd be good to allow Joe and Will to perhaps explain how they got into the industry with some of their sort of science and maths backgrounds as well.
Yeah, so I mean, I had an interest in maths and science at school. I did okay at GCSE level, but didn't really want to continue in the school environment after school. I wanted to go out and earn some money, so I started as an electrical apprentice, sort of working 4 days a week, and going to college. I started sort of wiring boilers and heating systems up for a local plumbing and heating company. That sort of progressed onto larger scale jobs. I worked for myself for about 10 years. I had some employees, again, on some larger projects, started to get more of an interest in planning and design of the services and how it all came together. That led me to sort of enroll on a foundation degree, which progressed to a bachelor's degree in engineering. Helped me, gave me a new challenge, new way of thinking about things, develop new skills. And, got a job 3 years ago now with ESD, and, I really enjoy it, challenging, but my time in industry has given me good experience that I can lean on when I need to in my current role as a design engineer.
As Joe, I started as, I did my GCSEs in math, science, English, all the basic ones, and I carried on and did my A-levels. I did maths, further maths, physics and biology. And then using those, I decided to go to the University of Liverpool, where I went for 4 years and I got a master's in physics. Whilst I was working, at university, I worked over the summers at ESD part-time, just to earn some money to be able to survive at university. I started off just being a CADS draftsman, so just doing the drawings, no the actual engineering. But as time went on, I did start to do more and more challenging stuff, some more of the engineering, the basics, and then more complicated engineering. And then after I finished my degree, John and the other directors were thankful enough that they offered me a full-time job, and because I enjoyed it, and I thought that I enjoyed doing the engineering and the challenges, that I decided to carry on, and I've been here since.
Thanks. And so how can you develop skills? I guess hopefully you've got a bit of an insight here into building services. It's it's a little known profession really, but it's got a growing reputation because of the impact that we're starting to have on buildings and the whole emphasis of the discussion on global warming and how we can control carbon emissions. Joe and Will are relatively new to the industry compared with me. I've been here for 40 years, but I've found that this is a job that you can get tremendous deal of satisfaction from being involved in actually seeing buildings that you've designed or helped design coming out of the ground and being used afterwards is a thing that you don't get in a great deal of professions really. There's a huge range of jobs that can be considered within the building services sector as well. You know, systems designer, consultant engineer, energy consultant, estimator, researcher, maintenance engineer, project manager. There's a whole range that all fall under this, that all need a good degree of engineering skill, a good grounding in maths and physics as well is a great start into this industry, as Joe and Will have both shown. Yeah, and the interesting thing now is it's an industry that can be approached from different angles, as Will and Joe just demonstrated. You know, either going straight to a level and degree, and then coming into industry, or having a trade, learning a trade, practical skill, and then moving into become a designer potentially. But there's also lots and lots of opportunities for apprenticeships now, we find. So with a decent group of GCSE results, moving into an apprenticeship and then onto college and university, ultimately aiming hopefully to become a chartered engineer, which is a recognised qualification equivalent to a doctorate within engineering essentially. Yeah. We have an institution, the CIBSE, Chartered Institution of Building Service Engineers, and they've really started to push on now with promoting building services as a career for younger students coming out of school and out of college. They hold Apprentice of the Year competitions now, and it's all a positive industry to get into with a really good message and like I say, great deal of job satisfaction. So there we go. Hopefully you found that interesting, a little bit informative as how your interest in physics at GCSE can be taken forward into a career in the future, and hopefully see if there's any questions that come out of that.
Just following on from that, John, if anyone has any questions, do feel free to put it into the Q&A box. I had a question actually. It was really interesting to hear what kind of projects you could be working on. I'm quite interested to know, and John, I'll just go back to you, and Joe and Will, you feel free to answer. But what's a typical day like for you? Is there a routine you follow, or is every day completely different?
No, I think that's one of the things I enjoy. I like Will and Joe answer that as well, actually, because we all do different things within the company. But certainly for me, there isn't such a thing as a typical day. There's lots of jobs out there where you know exactly what you're going to be doing when you walk into the office or your place of work at 9 o'clock in the morning. And that just has never really existed to us, but partly because we can be working on multiple projects at once, maybe up to 6 or 7 projects. They could all be at different stages of evolution. Some could be being constructed on site, some could be in design stage or early planning. And you never really know what's going to drop in on the email or the phone call that day that might have to shift your priorities around. And there are days when you can predict what you're going to be doing and it follows true to that, but certainly not every day. So some days can be calculations, some days can be drawing, some days can be on site, doing inspections of the work that you've designed. I don't know, how's that for you, Will and Joe?
Yeah, that's accurate, to be honest. You have meetings with clients or other design team members, working through calculations or producing drawings or basic, information for somebody to go and install what's being designed. As John mentioned, site visits. So yeah, it's good. It's varied. Challenging but good. Yeah.
Really quickly, Joe, as well. I know you mentioned that. I think you mentioned it at least. You worked for yourself for around 10 years. How have you found that transition back into working life, as in working in a team? quite interesting.
So I was contracting, so I was always sort of working in teams, building sites and stuff like that. It was more of a transition into an office environment for me that was different, because I've been used to, working on building sites across the UK, all over the place, really. It was coming back into education late, because obviously I'd finished college at sort of 20, and then for 10 years done no further education, and then back in a classroom at the age of 30. I'm 33 now. That was a bit of a challenge to pick up. That maybe would be a tip that I'd give my young, if I was giving myself any advice, just keep in education, really. I mean, it's good to do the course. Apprenticeships, I think, are brilliant, because you're learning on the job. A lot of the stuff you're going to pick up on the job, and you won't always learn the day-to-day aspects in a classroom. Yeah, it's good.
Sweet. Will, do you have anything to say on that last point? Do you have any last points on that, in terms of your routine, if you have a routine, what your normally working days like?
So it's just, as the other said, it's you're working on drawings, calculations, anything that comes up, and then there'll inevitably be a day when you're spending your day firefighting some issues that have come up that you're not expecting, and you spend your day all day trying to solve those problems. But that's just part of the challenges, and when you get it right, it works. It's good.
I think with the emphasis on this subject as well, Tevin, physics, it's not everything we do is physics based. Yeah, I mean, obviously, when you're walking around a site and looking at installations, or when you're producing some drawings, we're not applying physics principles at that point, but the understanding, the awareness, the interest of actually problem solving and getting to the bottom of maybe a difficult calculation, or a series of ongoing calculations to get to an end result, knowing that your results, I mean, the calculations that we do physics-based, that Will mentioned before about calculating out flow rates down pipes, we test out our calculations, because at the end of a job, we flick a switch, a pump turns on, it pushes water around the system. And if you don't get enough water around the system's not going to work. So the calculations have to be right. The calculations are proven and tested, and that's where you can get a great sense of satisfaction that the job you've done has been worthwhile and correct all the way through. So, and you wouldn't get that if it's not for everybody, and a lot of people go into our industry with more of a practical background, but certainly sciences, physics, maths are a great starting point, because you can apply those skills right the way through.
Sure. Thanks for that, John. And if anyone has any questions that is watching it recorded, do feel free to send over your questions to student@pathwayctm.com. That's student@pathwayctm.com. And that concludes our session for today. Joe, John, Will, thank you for attending on behalf of Pathway CTM. And yeah, it's been a brilliant session. So thanks again for that.
Thank you, everybody.
Thanks.
Cheers, guys.